a lot of problems with the spine happen from lifting loads or bending, right. So, these are two activities that we do on a regular basis in our everyday life, and you will hear about back. Large number of people will say they have pain in their back at some point or the other. Okay. So, let's look at what are some of the loads that arise, why is the back such a problem area, and how with a simple static analysis we can look at what would be the right way to lift a load, what is the wrong way to lift a load, and how what sort of loads is the spine seeing, what sort of joint forces and what sort of forces do the muscles have to exert when we either bend or lift loads. So, the first analysis that we will do is for a case where you can see there is a difference in the way the lifting of the load is happening in these two cases. You may have heard people say do not bend down to lift a heavy load, okay. Lift it, bend your knees and then lift the load. Okay. So, we will look at these different ways of lifting loads and see why bending your knees and then lifting the load is actually more beneficial or less harmful to your spine than doing it from a than just bending down to lift a load. As I mentioned, the erector spinae, these muscles will be the ones when you are lifting the load, those will be the muscles acting. When you bend your trunk, those are the muscles that are acting to prevent you from falling forward. Okay. So, that will be the muscle that we will consider in our model, and then of course, you have, and we will look at this joint here. We will look at the joint between the is called the lumbosacral joint at the base of the vertebrae, because from the sacrum it connects to the pelvis and transfers the load to the ground through the lower limbs. So, the spine, the L5 passes on the loading to the sacrum, which then passes it on to the pelvis and the lower limbs. So, we will consider this junction, this lumbosacral joint, we will consider that as a hinge joint and look at the analysis of a bending or a bending and lifting task. So, here is a person who is bending the trunk to lift the load. Person has a fairly, is not bending his legs. Okay. He sees a load, he just bends down to pick it up. Okay. Now, let us look at what the effect. So, and this is a picture to show you the joint that I am talking about, the lumbosacral joint here. Okay. That is the junction, that is the place where we are considering it here, right here, where you are saying that it is pivoting meaning it is a hinge joint there in the sagittal plane. I should not use the word pivot because in the context of the body we talk only about the rotational, although structurally both the hinge and the pivots are one and the same. Okay. So, we will consider a hinge joint at the base of the 5th lumbar vertebra with the sacrum. Okay. So, the question we are trying to answer is why you should not bend and lift. Okay. What is okay. So, if we draw here, if you look at this, you have the erector spinae muscle which acts like that. Okay. Then you have the joint force. So, I could say two components Jx and Jy. at the base of the spine. Okay. And then if I take the free body, I am taking this as my free body. So, that means I am isolating this part from the rest of the body. What other forces do I have on this? What other external forces are there on this? Where will that act? Weight of the segment. Okay. So, weight of, use a different color. Okay, so this is the weight of the legs. There is a ground reaction, right? And what is that ground reaction going to be? Let us say this is WL and weight of the person is W. So, what is the ground reaction going to be? It is W plus WL. Okay. So, that is how the weight of the body becomes. Yes. So, when you look at the whole body, okay, you look at the whole body and you figure out where on the foot this will act. Okay. If you take your free body, if you just separate it from the ground, then you have the weight of the whole body plus WL acting at a point, and this reaction will be directly along that line. So, where it acts on the foot will take care of that moment due to the upper body. Okay. So, this is now your, so my free body diagram is complete. These are the only forces that are acting on this. And let us assume that, okay, let me do this. Let us say my trunk, you saw the erector spinae muscles, right, they are almost parallel to the trunk. So, if my trunk is flexed a certain angle theta, I can assume that these muscles act at that angle theta. That is the line of action of that muscle. So, theta is your, in this case, your trunk flexion, the amount you have bent to pick up the load, and that is also the line of action. It also determines the line of action of the erector spinae muscle. Now, let us say I know these distances. I know the distance between the point of muscle insertion and the joint. Okay. Then let us say I know the distance between the joint and where this force acts. Let me call that B. So, if this point is O, my fulcrum, the joint, then I know the distance B, and then I also know this distance C from that to where the ground reaction acts. So, here we are assuming Fm acts parallel to the trunk, and therefore, that is the direction in which, so whatever is the trunk flexion, that is the direction in which Fm acts. So, now let us take some values. Let theta equal to 45 degrees, and I will give you these in terms of the height of the person. A equals this, B equals 0.08 h, C equal to 0.12 h. The this weight of the legs equal to 0.4 times the body weight, and then I have the load some load that I am lifting. Now, I can write, I can find F m by using the moment equation. So, I take moments about the joint. So, if I do sigma m o equal to 0 to eliminate the joint forces, I will have only the F m left. So, I will have F m equal to 0.12 h into W plus W L minus 0.08 h into 0.4 W divided by 0.02 h. So, I get this to be 4.4 W plus 6 W L. A is the distance between O and F m, the point of insertion. This should be A. A is the moment arm for F m. So, you can see that if the person lifts a weight equal to their body weight, okay, that is maybe too much. Let's say only weightlifters would try to do, but no, if you look at maybe lifting a kid, okay, who is fairly grown up, or you lift one of your friends about the same body weight, right? Or let us say we lift a kid, okay, about half the body weight, then you are looking at if W L equal to half of W, then the muscle force equals 4.4 plus 3, 7.4 times the body weight. What is your, quickly compute F j and F j x and F j y, or total F j. I have for W L equal to W, I have j equal to root of j x square plus j y square if I find the components. If W L equal to W, I have that equal to 11.7 W. What is it for W L equal to half W? Can someone quickly compute that? It is not very hard. F j x is minus F m sin theta and j y is W plus W L minus W legs minus F m cos theta. Why is it taking you so long to compute it? 3.3 is for j x, for which load? W L equal to W L equal to 0.5 W. For W L equal j y is 3.3, and what is j x? 5 point, okay, 5.2 W. So, the net magnitude is the magnitude of j square root of j x square plus j y square is 6 point. Are you sure? 25 plus 36. 6.3. Okay. So, j equals 6.3 times the body weight. So, that is the load that is seen at that joint, 6 times your body weight. If you lift something that weighs half your body weight. So, you can do a lot of damage to your back if you lift very high loads, and if you do not, and if you bend while you lift it. Okay. Next class we will do the analysis for a better way of, we will look at. So, you will see that even if you are not lifting a load, the next analysis that we do, we will see that just bending itself poses a lot of loading on the spine. So, if you had to work all day, you know, if your workspace was not designed properly and you had to keep doing something in this bent position, you will see that that can do a lot of damage to your back. Okay. Things have to be such that you can maintain good posture. So, if you have to bend, anytime you have to, your erector, because to keep your trunk from falling forward due to gravity, your erector spinae have to contract and keep the tension, okay, which leads to the joint loading. Yes.
The equation you wrote for JY,
Yeah.
W plus WL should be combined with a negative sign.
Plus
Sir.
FM cos theta.
Yeah, plus FM cos theta.
W plus WL, okay, plus FM cos theta. Okay. So, okay, I took JY as positive. Okay, let me just do this. Right, JY plus, yeah, minus FM cos theta. After I move it to the other side, yeah, that's what. Yeah. Yeah. 6 point? Ah, okay. This is 6.3 and what is the overall? 8.2. 8.2, okay, that makes more sense. Yeah. So, it's worse than we thought initially. Okay. So, that. So, we will look at more analysis with the spine and why it is important for workspaces in the next class.